Hi, everyone. Thanks for having me here. I hear I have a very hard act to follow in that Phil Woodler was the keynote speaker last year, so I'm a bit nervous. Even more nervous when there's this cliff here that I might fall off any time. And also, it's that experience of when you're sitting with friends at dinner last night at 7:30, and you say, I'm really looking forward to giving my keynote on Friday morning. And your friends kind of turn to you and they say, Friday. No, I thought it was Thursday. And so Thursday it is, but that's okay because it's all ready. So I want to talk about F-sharp code I like. And a lot of the examples that I'll be talking about today come from the F-sharp community. One of the really odd things, amazing things about being the designer of a programming language is not just the technicalities of programming language design and compiler implementation and tooling implementation and sort of working with the open source communities on making what we use, but seeing what people get to do with it over the years. And so thank you, a huge thank you to all the people who've just used F-sharp in so many different ways, so many different inspiring ways. For me, it's absolutely a huge part of why I've loved staying so involved and so hands-on and active in the language and the community right over since the time that we started. I will, however, also be talking about some code that I don't like, things that aren't in the F-sharp language design, things that aren't in the F-sharp library, techniques where people don't apply the appropriate technique in the appropriate place. I'll be kind of also taking kind of a middle position in a way, trying to reconcile functional and object-oriented programming and kind of carve out a path where we don't fall between the divide between these camps quite so much. And all along, that's kind of going to relate to some of the language design. And part of this is because I've been writing a history of the F-sharp programming language for the HOPL conference. So HOPL is a great conference when you're writing a paper for two reasons. Well, it's an interesting conference, first because it's only every 10 years that it's held. And so, HOPL only comes along now and then, and you have to, when there's a chance to submit to it, you can't delay, you can't put it off till the next year and say, I'll do it in 10 years' time or something. You've got to capture it now. And the other thing is because it's actually trying to capture source material in a way. You don't have to fully reference everything that happened along the way. You can give some personal anecdote. And even better, there's actually no page limit for the submission. You don't have to kind of do that horrible thing of cutting large chunks out of your paper in order to squeeze it down into the 12-page limit. So if you're interested in a 40-page history of F-sharp, I've just received the first round of review feedback on this, so I'll be folding a lot of that in. But it's available here at fsharp.org/history. And please do take a look at that and send me feedback, and it'll be folded in if you've been involved in F-sharp, or if you've got other perspectives from other functional languages, and you look at the history of F-sharp and you remember something from it. Please do let me know. Now, part of the telling the history of F-sharp, the point where I start in the history of F-sharp paper is the creation of the first versions of the ML programming language. And it stretches back to roughly 1970, 71, 72. And I'm sure for those who are into psychology, I'm sure it's no coincidence it's around about the time I was born. And my own story begins about then. And you kind of you look back in history, and that's where you start telling kind of the story of where F-sharp as a language sort of came from the ML family of programming languages. Of course, there's a long history before that, and there's many other threads of history in between as well that led to the creation of F-sharp. My own personal story was that I'm from Australia, and I went to university in Canberra in Australia, and my supervisor was Malcolm Newey, who was one of the first 3 people who worked on the first version of the ML programming language in around 1972, 73, 74 in Stanford and in Edinburgh with Robin Milner. And In many ways, I got exposed to the ML programming languages through him at university. I learned to love them. I learned to love functional programming through that route, and that heavily informed the creation of F# at Microsoft Research in the 1990s. Part of the story that I also tell, and I think it's one where a lot of people will have who are my age will have their own version of this story, and that's the story of the intersection between. It's a story of what I call the object-oriented tidal wave in the 1990s. That this sudden wave came over the computing industry that everything needed to be an object, more or less. Everything needed to be, every language needed to support inheritance. Every academic agenda needed to have an angle about how to do the object-oriented thing in their particular kind of part of the world, and that affected programming language theory. It affected everybody making programming languages, everybody using them, everybody designing libraries or tools for them. And there were many different reactions to that. You can see Scala, for example, as a reaction to the question of object-oriented programming and functional programming to some extent. But that's not the only kind of reaction that people had. People brought in many different things. And again, that's covered in the history paper, and it's related a lot to the themes I'll be talking about today. So please do take a look at the history paper. Now, the history paper is opinion and personal story, and a lot of this talk is also opinion. So I want to talk about F# and F# code of love, but I better tell you a bit about F#. Okay, so what is F#? Well, if you go to the F# is open source. It's independent. It has a software foundation, the F# software foundation. There are companies that contribute very heavily to F#, and one of them is, of course, Microsoft. And this is Microsoft's point of view on why it contributes to F# and why it packages and makes F#. And that is that F# is the open source cross-platform functional language for .NET. And one of the interesting things about F# is that as you come to it from different angles, you can actually now have quite different perspectives on what F# is. And this is Microsoft's perspective when you're coming at it from the kind of .NET, the .NET angle. But if you ask the F# community, in particular the F# community doing web programming, then a lot of their perspective on what F# is actually now through this thing called, oh, my clicker's not really working, but I'll point there, this thing called Fable, which is F# compiled into JavaScript. And unlike many transpilers, it doesn't really have the feel of a kind of an odd thing to do to F#. F# is actually very close in nature to JavaScript in its compilation line. The JavaScript code that you get out is actually very close to the original F# code. And so Fable is also fully packaged and delivered as a node package. Okay, so you do tend to use F# on the server side as well. In its F#.NET on the server side and F# Fable on the client side, and you can share a lot of the code between the two. But when you sort of culturally, you can come to F# as a JavaScript node programmer, not as a .NET programmer, and you can be very happy working with the Fable toolchain. So although many people would probably over history think of this as F#, there's also this angle on it, and you can come to it and be happy with that. So to roughly go over where we are now. So first of all, as I said, F# is open, cross-platform, and independent. I kind of can't read what's on the screen down there, so I'm going to have to keep looking up there. So everything's open source. All the F# language, all the F# tooling is accepting contributions. And the F# community very self-empowered, and through the F#, what we call the F# Software Foundation, which is a non-profit organization in the United States. In terms of professional tool chains, we have Xamarin and Visual Studio for Mac, .NET Mobile is F# tooling for Android and iOS. You can also use React Native. We have Visual Studio Code, and a wonderful F# toolchain, which is fully open source and actually now funded by the F# community itself. There's been a fundraising effort recently. We have Christoph here in the audience, who's one of the people who will benefit from that fundraising and be able to continue to work on the toolchain. That's called Visual Studio Code. And then we have Visual Studio Mac for Windows and Mac, and lots of other editors that you can use. And we also have Visual Studio Code and .NET Core for Linux and iOS. Now, underneath, we have a component called the F# compiler service. Now, this is a single component, which is the implementation of F# and all its tooling in terms of IntelliSense and autocomplete and interactive evaluation. And this single component is used to build nearly all these other components up above. We have Fable, which I've already mentioned. And lastly, this story over here, the fact that F# is sort of no longer, F# grew up in its sort of version 2, being tied to Visual Studio, but that's long in the past now, and F# is now a normal programming language in the sense it's not tied to one IDE toolchain like it was back then, and we're just fully open source and fully normal and cross-platform, and that's allowed me to focus on the F# language design over on the bottom right, and that's F# 4.6 has just been delivered. We've done 4.5, 4.0, 4.1, 4.5, and 4.6. The language design process is fully open. You can check it out here for FSLang design and FSLang suggestions. You can make contributions, implement features, work on RFCs, and the like. Just to give you a feeling for what's been going on in the language, I won't go through this in detail. F# 4.0, you can scan over the list there. F# 4.1 was lots of work on unboxed structures and performance. F# 4.5 was on integrating with some features of .NET, span of T, and async debugging. And we put out 4.6 because one thing didn't quite make it into 4.5, and that's this anonymous records. And so we got that in on the next train that we could deliver. I've talked about VS Code and INI. That's the one that so you don't have to use Visual Studio. You can use many different editors, but VS Code is an absolutely much loved one that people are actively contributing to. .NET Core, if you're on Linux and you want to get started with F#, you just type in .NET new lang F#, and then .NET build in the created project, and you're off and away working with F#. Okay, and I want to talk. So in the reconciliation between object-oriented and functional programming, one of the key things about the ML approach throughout its history, and especially for the F# approach, is what I characterize as functional first programming. So F# is not only a functional programming language, it's also an object-oriented language, it also can be used as an imperative programming language. But your functional programming forms your sort of first point of call for how you solve problems. It's not how you have to solve everything, it's not how you represent all information, but it's your starting point for where you begin with your journey. And so, this matters a lot because in many ways, F# technically supports many of the features that, say, C# does as well. We have to for interoperability purposes. But the question of emphasis matters hugely in this. The question of methodology. What methodologies are you supporting? What's normal in F# programming? And I just want to talk about how this actually does make a big difference in practice. I want to use one case study which, although it's obviously not a controlled case study, there are a lot of controlled variables in it. They're using the same runtime underneath, the same set of .NET libraries underneath. They're working on the same business problem. And that was a case study done by, written up by a guy called Simon Cousins. And it's from the UK energy sector. And it was basically two teams were implementing more or less the same functionality, an offshore team and a UK team. Now, there are cultural differences between these teams. There might be some experience differences as well. But the offshore team was done, we're using C# and using all of the C# sort of design patterns kind of thing. I mean, there was everything in here. Simon's measurement was that there were at least 4 different implementations of the dispatcher design pattern hidden away in this 350,000 lines of code. And that's really odd because there's already an implementation in .NET. So they were just kind of busy re-implementing design patterns again and again, and thread pooling and everything else that was needed to be implemented multiple times. And then we had 30,000 lines in the F# implementation. So the C# project took about 5 years to complete. The F# project took less than a year, had at most 3 developers to 8 developers. Only one had prior experience with F#. If we look at some statistics as we go through this, we have 56,000 lines of braces there. It must have taken a long time to write. Lots of null checks, 3,000 null checks in that code. So 3,000 sort of failure points, you know, where you've got to be kind of worried about what's going on there. We have lots of comments, that's good. And then the useful code, etc., app code, and summing it up. Okay. Perhaps most tellingly, I think, this is the number of try-catch statements. The number of places, we had 2,000 try-catch statements, 2,000 places that could have raised an exception. And it's odd because they had what, 40,000 lines of test code, and each test takes a fair bit of code. So they can't possibly have been testing all of those particular failure points. The F# code had something like 9 or 7 try catches. And I think what had happened, C# people were implementing an asynchronous system, and they started getting exceptions in some of the asynchronous callbacks, and they weren't properly using the C# async feature. They essentially started having to put catch handlers around absolutely everything because they didn't, when something went wrong, they didn't know where to send the exception. They didn't have any. So it's a place where you just end up doing defensive coding at every single point. And obviously the complexity is completely out of control in this project and was ripe for re-implementation or redesign from using F#. Simons is particularly proud of delivering projects where he had 0 bug reports after delivery, and he claims this project was 0. He's particularly proud of a Friday afternoon tweet saying, I've just delivered to production and I'm off to the pub. Because nothing's going to go wrong, or something like that. So I don't really believe him, but he did say in this one there was 0 bugs in the deployed system, and that means F# is totally the safe choice for this kind of project, in this kind of sector. Okay, and just to say one other use of F# in practice, and that's the major, huge use of F# by a company called Jet.com, which got acquired by Walmart at a valuation of $3 billion. They're also, from Microsoft's perspective, very major users of the Azure cloud platform. And of course, if you know about the business that Microsoft is in, that's a very major focus, business focus for us, and in many ways is the kind of business rationale that underlies .NET and F# and C# today at Microsoft, and a lot of other things. A lot of other tooling we're doing at Microsoft, including in Python, including in Java, a whole range of different things, all to support the use of the Azure cloud platform. And so from our perspective, working inside Microsoft, this is a very important motivator that not only were they acquired for this kind of value, but they actually do help pay the bills at Microsoft. Okay, so let me talk about code that I like and I don't like in F#. So a lot of this is taken from the F# Advent calendar. This is this really fantastic F# community effort that's run every year. And it was actually started by the Japanese F# community. So if I've got it right, there we go. That's a screenshot for those who speak Japanese. You can see or read Japanese all the different entries. I think this is back in about 2015. And in many ways, it makes writing a talk like this easy because it's a point where the community, the end of the year, and they've already been thinking about this all year. Just last night, we were discussing some funky ideas for the F# Advent calendar for the end of this year. It's a time when you kind of think back and you think, what part of F Sharp, my working life in F Sharp or my hobbyist programming, what part am I most proud of? Well, sometimes they tell stories where things didn't work out as well. But they talk about what code was the most beautiful or the most, the most inspiring part of my year. And so it's a great resource for a talk like this, and you can just go back over any of these Advent calendars, and it's just so many amazing blog posts, usually 2 per day during the Advent season from different members of the community. Another point for me to start was to, as I went through the history of F Sharp, was to dig out the old slide decks and dig out the old posters from the 2000s and see what I was talking about when we started off with the design of F Sharp. And here's one of those really old slides. You can tell because those buttons have all got that kind of round thing on them. And this was how I described F Sharp, I think, in 2006. And it was, a key thing about F Sharp is not, it has the core of the ML programming language as part of its implementation. But the key thing was always not, I don't even mention the word functional on this slide, for example. We decode what functional programming means, and we place functional programming in the context of practical programming with .NET. And so F Sharp is statically typed, so that's part of the functional thing. It's succinct, and that's part of the type inference thing. 2 of the core values of strongly typed functional programming, going right back to the 1970s. When Robin Milner started ML, he wanted those 2 things. He wanted, I want a language that I can use to code complex tasks in the context of theorem proving, but it's got to be statically typed because I don't want to deal with all those mistakes. And it's got to be succinct because they can't possibly write swathes and swathes of the kind of code that they were having to do before. Okay, so those 2 are core values of functional programming. But now we want the other properties that we need to mix. And this was inspired very much by Phil Wadler's paper. It's not actually a widely cited paper, but it's a great short read, which is why no one uses functional programming. Okay, there's a paper from the 1990s. It's called, I think that's it. It's basically 7 reasons why no one uses functional programming. And he covers those. It's a bit of a point in time thing, like why no one was using it at that particular point. But it's still worth reading, and it's still, because it deals with these practicalities such as libraries, and libraries and interoperability in particular. Okay, so we want to be able all these other things. We want to scale, and back in the 2000s, this meant scaling over multi-core. Now it means scaling over multiple machines. We want all these other things as well, libraries and efficiency. So it's fair to say that the point of F Sharp is that we want these kind of properties. And the F Sharp code I love fundamentally has these kind of merits. Okay, so to start with something that's actually not a functional program, something which the Haskell people will here kind of have a heart attack over because there's no, it's having a side effect here. Yeah, so you can do side effects in F Sharp. It's an impure functional language. That's a short little program to print hello world. And it's succinct, expressive, and it interoperates. It's using the .NET libraries underneath. It has, its performance is good and so on, and low bug rates. That's nice, a nice start. Okay, so F Sharp code has lots of this kind of pipelining kind of thing. You'll see this endlessly, and people, you'll see this almost every second line in F Sharp code. Usually formatted over multiple lines. You'll take some value and you just pipe it through a whole lot of functional transformations over so from left to right, like this. And so, this kind of code is a joy to read. We're filtering, we're doing a parallel map over some of the symbol uses, and then doing filter, then a group by, and then a map along the way. Okay, so that's at the sort of core of functional programming. Lambdas, tuples, although they're not shown here, functional programming, lists and arrays, and sort of the core of the F Sharp language is built up from that starting point. Now, when you look through the F Sharp Advent calendar, a huge probably about half the entries, or even 2/3 of the entries, are in the area of what I'd call domain modeling. And from a historical perspective, this is also interesting, because when you go back to look at why they created the ML programming language to start with, it was to do domain modeling. They had a domain that they were interested in, which was theorem proving, what they called LCF theorem proving. And they wanted to model the elements of logic, the terms of logic, and the rules of logic. And they wanted to package that up in a safe, trusted subset, sort of put an encapsulation boundary around it. And then they wanted to program and program and program up the rest of mathematics based on this starting point. But you have a domain that you have, you need to model it, and then you program up everything from that point. And in many ways, so there's another kind of example of programming up expression trees. You know this sort of thing if you're into functional programming. And then once you have your domain of logic expressions here, propositional logic, you just program up everything after that. You just start programming up all your different analysis and visualization and tools and so on. And so for myself, working in the context of the F# compiler, here's a little domain that I need to work with. This is the information the F# compiler, the F# optimizer knows about your code. So it might know that one expression is actually equal to another value. So whatever it is, it's equal to this value. It might know that it's a tuple, a record, or a union case, or a constant, or it might know that it's a lambda of some expression over the right. So this is what the optimizer knows. And you can more or less imagine if the optimizer knows this about your expressions, you can actually kind of work out what kind of optimizations it is going to do. And the rest of the optimizer is just sort of built up, starting with this modeling of your domain. And here's another typical bit of domain modeling, just taken from some blog post where you're modeling the responses from a website. I mean, here. And Luke here says, F# has lots of strengths, but this core element of domain modeling is at the sort of the heart of so much of what people do in practice with F#. This sort of practical information representation, and then programming the rest up from that point. Udi from Nigeria here is talking about here modeling the information coming out of, I think he's downloading his iPhone playlist or something from Apple, and then working with the information that's coming from the Apple web service. And he makes the interesting point that the core design of this of these domain models is absolutely critical. If you get this right, then everything goes well. And if you get this wrong, then you kind of walk around in the weeds for a very long time until you land at the right design that represents the domain and allows you to do the programming in the most efficient way above that point. And so, of course, this has been long known in the functional programming circles. The use of discriminated unions to represent information is not a new thing. But what F# has allowed to happen is to bridge this with the world of programming practice in many different areas, and to bridge it with themes in software engineering discussion that previously that I wasn't able to do. The F# community have been able to start with this functional programming base and take it out into many different realms. And one of the people who's doing this best is Scott Wolashan. And he's got this book called Domain Modeling Made Functional, or Domain-Driven Design and F#. And in many ways, this has allowed F# to enter the discussion in the kind of architects kind of point of view. So you don't have to do the old UML thing or the other variations on architecture and modeling. You can just say, well, just start with your code, start with modeling in code. And many of the elements of your old way of thinking from architectural thinking can actually translate into just practice of coding up a domain model. And in a sense, what those of us who use functional programming experience, where you start one evening to work on a problem domain and you crack out the essence of a solution to that problem domain as code, and that forms the basis for a team to work with from that point onwards. And it's that kind of experience of domain modeling, the introduction of domain semantics, and carrying that through that book is trying to capture. And another book I'll mention is this Get Programming with F# by Isaac Abrams, which also focuses heavily on this sort of domain modeling angle. Okay, so I'll talk about another completely, somewhat different kind of code that I love. So domain modeling is a huge part of F# usage. Another area where we're seeing growing F# usage is in view modeling. Okay, so, or in functional programming approaches to app and web development, web app development and web UI development. And now this bit of code is taken from a system that I worked on last year called Fabulous. It's out and open source, and it's a mobile programming framework for Android and iOS. And this is where we're using functional programming, and we're using what we call the model view update architecture. It's the same architecture used by Elm, and we're taking that to the world of mobile app programming. So this is a view function. It's a dynamic view here. So every time the model changes, we reevaluate the view, and then we say if the model was pressed, we're going to show a label, and if the thing wasn't pressed, we show a button with the command to dispatch the pressed message here. And so that's model view update mobile app, at least a view part of it. And here's a web app here. A very similar thing. We have the view model dispatch, and if we look at some text, and we show some divs here, and otherwise we show a range of other divs with container, button, and click, and text, and so on. Again, that's a model view update web view. So you can check this out on the mobile angle of this at this website, Project's Fabulous. And the web version of this is based on Fable and a library for Fable called Elmish that you can use for web UI development. There's a range of apps here that have been built using Fabulous. And this is all built using this functional view technique underneath. This is used functional view technique combined with a library to specify 3D animations. And this sort of, the top left is a sort of toy game example over on the right, and the bottom shows the interoperability and integration with the map library over here on the right here. So just to talk a little bit about this model view update architecture, this has been one of the things that I got wrong in the history of F#. When we did F# in 2005, 2006, when we started it, I had no sense that functional programming was so relevant to user interface development. And in many ways, I talked about the object-oriented tidal wave of the 1990s. In many ways, that was driven, but that was the era of the widget, the era of the object-oriented framework for creating UI controls for applications on Windows, or applications on Sun workstations and such the Next Step and other systems. And in that world, a button was an object, the label was an object, everything on the screen had to be an object, and that was where that object-oriented thing kind of came from. But I had no sense then that using a functional approach to user interface development could be so effective. And Elm here has really shown the way for functional programming to be relevant in this domain. And it does it using a pretty brutal technique, which is called view reevaluation, where you actually are willing to reevaluate this view on every change to this model. And then you reevaluate the view, you get some divs, and then you apply them differentially to the actual display. So if the view, you keep the last view and the new view, and you do a diff between the two, and then you make any actual changes to the underlying view. But it does mean you have to have modern computing systems which can, these views aren't big. The view reevaluation is not that expensive, and there are ways to optimize it to make sure it doesn't do much reevaluation. But if you're willing to do view reevaluation, then your view just becomes a functional program. And that's an amazing, amazing simplifying thing. That given your model, you can just do a whole lot of functional programming to generate your view. There is no state in that system. Well, there is state, but it's being managed for you separately through that differential update process. And this idea is something I had no inkling would be so effective and so practical for such a range of web and mobile app development. And I think even in the last 3 months, I've been having conversations with people at Microsoft, kind of communicating and helping them understand that there are different approaches to web and UI and mobile development, which don't have to be so object-oriented. Microsoft is very heavily invested in this idea of object-oriented user interface development. And for those of you using React, those of you using Elm, or any of the F# variations on that, you'll know that it can be much, much simpler to take the functional approach to this kind of development. So this is an ongoing conversation in Microsoft and throughout many different programming communities. Just to say, I'm really, really shocked and really pleased how effective F# is and functional programming generally is for user interface development. And it's really going to change the story about functional programming in that area. Okay, F# code composition. Here we go. It's a beautiful little bit of code for the top level of a compiler. We all know this sort of thing, that you just compose the phases of a compiler. You can see here this use of this railway map programming for handling error cases coming out of the bottom. So nice little sort of functional composition libraries there. This is sort of the same kind of compositional approach taken to web server programming. We have our sign-in and our redirections and our choosing, getting, routes for the top level of a web app. Okay, so that covers the essence, the core features of what I absolutely love about F# programming. The core functional nature, the pipeline programming, the domain modeling, and the composition and the practical problem solving that people do with that, and then the view and user interface code. I want to talk now a bit about some elements of functional programming that I don't like and that don't feature heavily in the F# language design. And it's not heresy. We should all be quite willing to say that not all functional code is good code. Okay? That those two things, functional is a technical feature, good is a quality, a virtue, and that functional doesn't mean good. And so one thing that I don't particularly like is these two little babies that you see in lots of functional code. F# does support curried function application. You can do F, X, Y, but we don't have these library functions curry and uncurry to automatically convert between the two. You can write them yourself. They're just 2 lines of code. If you really want to use them, you can put them at the top of your code and scatter uses of curry and uncurry all the way through your code as much as you like. In essence, by not putting them in the F# library, I'm saying that we don't, that their widespread use just leads to unreadable code, effectively. That leads to this sort of obscuritous tendencies in functional programming where the meaning will be hidden behind this magical sort of magical set of combinators which only the gurus will know what they all really mean, and if only you could really divine inside them, you could understand you would reach a sort of new level of knowledge and existence. We don't take that approach in F#. We want our code to be simple and plain and debuggable. Performance is known, and you know what you're getting with F# code rather than being hidden behind this sort of layer of obscure combinators. So one particularly bad example of this that I saw was an intern came to Microsoft. I won't say who, it's a long time ago. and was obviously totally in love with the idea of currying. That they would take these .NET functions like string.compare, which is normally written like this as a tuple function, and they thought there was some virtue in using a curried functional application over tupled application, which is what we use for object methods here. So this person would curry the string.compare and then apply it to the two arguments. A completely crazy thing to be doing in any setting. Why not just apply the tuple? But that's an extreme position, but it was a real one. I was faced after the intern had left with removing pages and pages of currying from their code and reducing what was about 3 pages of code down to 1 page of code because and what was just very simple .NET interoperability code in its essence. So yeah, code is not some sort of game where you kind of try to where you choose some ethic like curried good and tupled bad or something and apply that all the way through the code in some systematic but obscuring way. The F# approach is saying, well, tupling is totally fine in those argument positions and totally normal, and you're going to see an awful lot of this. So also we don't really do this sequence map uncurry F kind of thing. If you instead just make those, it's just, this one's okay if you know the meaning of the things, although even I have to kind of always remember uncurry, curry, which way around is it? And instead just put the lambda in here to make things explicit that you had a tuple, the zip creates tuples and you get a nice tuple here and then you apply the function. It's just better to do it that way around. So you can tell from that point-free programming is not particularly an aim for F# code. I actually got a slide on that in a moment. Another one is this backward pipe operator, which was basically a bit of a mistake in F#. We do allow it, and Haskell people will recognize this, of course. It's used heavily in Haskell. This is a sort of mess that you'll see people doing. They'll pipe forward, and then they'll pipe backward here. I actually can't even remember whether this, which way does this associate with? Does it associate here, or does it associate with all of those? And, and the thing is, you just don't do it. Some people call this the TIE fighter operator, when you put these two things here, and you look like that. Okay, and instead, I think in this case, this thing wasn't actually needed, if I've got that correct. So, right. So, in general, I kind of say, if you're doing F# code, just don't use it, and certainly not in beginner code. It's just not worth losing the beginners at that point. And in general, there's only a few places where we actually use this in practice in F# code. So I would just say, just don't do it. And if you ever see those two operators on the same line, then that should just be ruled out in the F# compiler right at the start. Right, and even worse, I put in these two things here, which is sort of the 2-argument and 3-argument versions of these things. There are 2-argument and 3-argument forward piping operators, and we do use those quite a lot. They're quite nice. But these ones are just out. Okay, they should be deleted. They should be removed from the F# library, and never used. Okay, so they should be deprecated. Okay, so point 3 you can see is not a virtue particularly. So the point 3 is code without explicit lambdas, and if you like, even without a let binding. And it often involves, you've seen some examples, some very nice uses of composition, function composition, which is this operator, this sort of clearly bind operator here, curry and uncurry and partial application. Now, we do some of these things, but this is the sort of stuff you see even in beginner samples, and we say, just don't do this sort of thing. List.map, and the plus operator applied to 10. Double the answer times 2 plus 1, sort of composed with plus 1. It's cute, but I just say, just don't do it and avoid it if possible. And just write it the obvious way. Add 2x is x plus 10, and double an increment is x, and x times 2 plus 1. This is just so much better, so much more readable. And if you compare the number of uses of the function composition operator in Haskell code to F# code, you'll see that F# code will have far fewer uses of explicit function composition, this double operator here. I did show you one before of the composition of the stages of parsing and compiling and optimizing and so on. That was a fairly good use, although it wasn't particularly necessary even in that example. So in general, people will instead make the argument explicit and use the pipelining operator. So in F#, you'll nearly always make these arguments explicit. And there's lots of good reasons for doing that. Code readability, but also it works much better with the debugger, that you can put a breakpoint over on the right here. When you hit the breakpoint, you can see the values involved on the left. Okay, and Eric Tsapalis has a great blog post on this. In rare cases, there can be point-free DSLs that are actually legible. However, the utility of adopting this approach always carries a big burden of proof and should not be motivated merely out of stylistic considerations. So there has to be genuine utility in adopting a point-free style before you go down that path. Okay, fold. You'll actually won't see much use of fold in F# code. Again, I think if you compare Haskell code to F# code, then you won't see anywhere near as many uses of fold. So it's a very blunt instrument, and I actually think of it as a bit like a go-to in your code in many ways. You've got to really look at like that fold and what's the state? It's the introduction of this state being passed through an operation that needs to be decoded. And in many ways, when you use fold, you're kind of doing imperative programming because you're introducing state that you have to consider as it gets passed through. And so in F#, you'll nearly always use these. There's a wide range of other operations, sum by, max by, choose, try, pick, map, fold, and reduce, and so on, to avoid using an explicit fold here. And you can do some nice coding like this, where you say, usually the inputs go on the left here. You have the state and the elements, and we're folding over a list, and we have the state and the x. If you are going to fold, you generally write it like this, and then we double pipe because we have these two arguments coming in over here. Okay. And sometimes folds can be harder to understand than an imperative version of the same code. So fold can sometimes be harmful. Okay, and now let's start talking about data representation in records. So F# supports record types, but it also supports object types. And also supports record types where you can extend the set of available operations to include extra members, extra outputs from the record type. So every time we design a type, we design an external view and a sort of internal representation. And records tend to be good, but in the specific case where those are the same thing, or maybe there's only a little bit of extra information available in the external view. Okay, yeah. But when they are not the same thing, when the representations internally are different to the external presentation, then you probably want to avoid things. Now, I actually don't have a really good example of this, but I just want to say that means records. Often you'll start with records in F# code, but then you'll transition through to objects as your internal representations need to change for that information. Okay, just to give a particularly bad example of the use of records, where the internal representation is not being encapsulated. Now, this is a mutable data structure. There's lots of these refs. This is ripe for using object programming to capture this. And it would be much better to replace this with an object type, which makes that mutability explicit, which encapsulates the use of this, and then allows controlled access to this kind of code. And so some systems programmed with F# or ML try to use this because they think that records are somehow a virtue, but they're not in this case. You should not be using records. and they're not a virtue in themselves. You should just embrace controlled use of objects. Okay, so that brings me to the topic, which will be the last one I talk about, which is about objects good and objects bad. Just to show what object-oriented programming even looks like, or object programming looks like in F#. We have vector, we have some inputs at the top. Again, the clicker's not working. We have, I'll run through the little bubbles here. Inputs, we have object internals, we have exported properties, and we have some exported instance method down here. And the v parameter, v dot, is just giving a name to the self, the this parameter on the right-hand side of each member. And this is what the language constructs are. We have integration with expression-oriented programming, but have these object expressions over on the bottom right. Okay, I'm actually going to skip these. So the thing about if you're going to put object features into a functional language, sort of the starting point of the agenda in the 1990s for both academic and applied research is to deconstruct what this object-oriented thing even actually sort of is in practice, because we don't want to take all of object orientation into F#. We don't want to make it an object-centric, an object-oriented programming language. And so that means you have to pull apart object-oriented programming, deconstruct it into each of its little elements, and work out how all of these things kind of interact. And so, you know, kind of you pull them bit by bit, all the different things, and the things that come along with object-oriented programming, such as idioms like iDisposable or iEnumerable in .NET. Some of these are .NET things, but they're all these different aspects of OO. And the thing is, what do you do with this big sort of soup of features? Because some of them are genuinely useful, okay? Object APIs, .NET APIs are very well designed, and they use the elements of object programming very tastefully. So some of these things would actually make F# a better API language, genuinely, in and of itself, independent of the .NET. The dot notation is genuinely useful and simplifying. So some of these might make it a better implementation language, like struct representations or some of the other elements. Some of them are part of the world we live in, whether it's .NET programming or JavaScript programming, and some of them are not needed at all. So how does this sort of break down? So, well, more or less, we embrace a set of things, such as the dot notation. We embrace the kind of object programming I showed before, and some things like named arguments and optional arguments, index and notation. So many of those things to do with making F# a better API language. And then there's a set of things which we have, but you use necessary, you use tastefully, you use sparingly. Mutable data, we're functional first, but you can do mutable data. There are patterns like iDisposable, iEnumerable, you implement those where necessary, and the interoperability elements. Then there's a set of things which you don't do, which are kind of going down the object-oriented rabbit hole. Okay? And that means large type hierarchies, implementation inheritance, nulls, and method overloading. So those are, you can do those in F#, but you don't. They're heavily de-emphasized in the F# world, and you pay quite a large penalty in just syntactically in your F# code, deliberately, when you start doing these things. If there's one thing I really strongly dislike about object-oriented programming, it's the hierarchy-oriented thinking. That this idea that this type hierarchy plays such a central role in the design process. That disappears from F# code. You very rarely think about the hierarchy of types and implementation inheritance in particular when working in F# code. Okay. And just to say that we have a set of things here which are not supported at all. A couple of feature interactions we don't support, and then sort of wildcard types, aspect-oriented programming, or whatever, a whole range of other object-oriented things that aren't in focus. So to me, and if you've been listening to what I've been saying, I've corrected myself several times. F# supports object programming. It is not an object-oriented language, and that is crucial. I really want to get rid of this object orientation. F# supports object programming, but also supports sequence programming. It also supports async programming. It also supports straight up value-based functions and tuples, the sort of function and the core of the functional programming language kind of model. And object programming is just another kind of programming that fits pretty well with all those other kind of things. And I'm willing to embrace that, but it is not an object-oriented programming language. And object programming has lots of positive virtues, and we should be willing to embrace it appropriately. And that's good API design, good naming, practical encapsulation, composable abstractions, expression-oriented, and crucially, making simple things out of complex foundations. Object-oriented programming, especially the implementation inheritance view of it, has objects as everything, a sort of mentally dominating single paradigm, has this endless focus on hierarchical classification. Large abstractions, often with many failure points, and composition through more and more hierarchies. And crucially, when you do implementation inheritance, you're making something that's already complex even more complex. That's the definition of implementation inheritance. And that's what I really dislike. It doesn't have this simplifying effect, this encapsulating effect that a good object or object programming should have. So the F# approach is to embrace object programming, make it fit with the expression-oriented paradigm, but not full object orientation. Okay, I'm going to skip this part here. And just to say, there's one other, I mentioned sequence programming in F#. Oops. So that's in this general F# language feature called computation expressions, or the sort of, it's basically the monadic or monoidal syntax in F#. So you can do sequence programming like this. So if you take a look at this code, which is sort of, we've got list.concat, list.filter, collect cons, filter. You kind of look at all this code and you think, well, couldn't this kind of be simpler? And in F# you can just replace this with this beautiful use of this sort of sequence-generated list here. We have a list here. We're making a list of things, but we're allowed to do computation. We're actually allowed to do for loops here. We're allowed to do yields here. So this is our comprehension syntax, but it's a very, very general syntax that allows the use of this sort of yield in under all these conditionals, and then to yield another entire sequence here, actually recursively yield elements of this list here. And it's actually very, very nice code and very, very readable. So that's just one use of the computation expression syntax. You can do async programming, just to do one example here. We have async blocks, these curlies, async curly here. And you can do asynchronous sequences. You can do all the sort of usual monadic kind of syntax thing, but you have this very rich monadic syntax to allow you to, monadic and monoidal syntax to allow you to express all these wonderful little computational devices. Okay, just to add some final virtues, I've mentioned some of these along the way: performance, debugging, testing, commenting, software engineering concerns, and readability and sort of integration with systems like CI. I'll skip those. Okay, so just to close, F# emphasizes clear code to solve real-world problems. That's really what the essence of the design is. Code that does that is the code that I love. And just those two things, sort of the two balancing points. Okay, not all functional code is good, and object programming has many positive virtues, but you don't have to embrace all of object-oriented programming, either in your practice or in your design. And that's it. Thanks very much for having me.
How do you resist the temptation to add more syntactic features in F#? Because there are a bunch of functional languages that keep adding syntactic features, which sometimes makes sense, sometimes doesn't. How do you handle that in F#?
Well, procedurally, we have this F# language suggestions, where anyone can file a suggestion and anyone can comment on the existing quite large number of suggestions. Every 3 to 6 months, I go through that and trim those suggestions down. I say no to things. But you're right, we do get a lot of suggestions, but to be honest, the core of F#, it's based on this very, it's based on the core of the ML programming language, which was as adopted into the OCaml programming language, which is now the core of a very stable core. F# code from 2003 continues to work and compile today. It's like, I don't feel the pressure to change those core constructs or just extend more and more kind of cute features. The set of features that we have is very rich and powerful, and I don't feel that, certainly in the expression-oriented core, I don't feel that there's a lot of need to be embracing many additions or changes. There are things absolutely want to work on. So F# doesn't support type classes. Okay. So we do, one of the original motivators for supporting type classes was to do monadic programming. Well, two things, general monadic programming and overloaded arithmetic. F# does support overloaded arithmetic, and it supports generic overloaded arithmetic as well through the use of, where you can look up the inline features that we allow there. But there are some areas of use of type classes which I'm still interested in solving over time. And so that is a tricky area to solve completely in the context of F#, in the context of object programming, in the context of .NET and its library design, because it overlaps and interacts with how you do library design. So, but there are still some elements of the language design which we will definitely progress. But in essence, we're at version 4.6, and it's a very core, very stable, very happy with where the language is at. Yeah.
Oh, hi Don. I have the microphone, so maybe.
Sorry, where?
Hey. So you spoke about these two projects, the C# project and the F# project. How much of, or how many of the differences, or how much of that difference do you think is down to the language that they use, and how much do you think is down to just good software engineering?
I mean, through the talk, I haven't been fully separating those things. I haven't just been talking about F# as a language. I've also been talking about F# as a mindset and a methodology. So I think if you're going to offshore your IT project to some other group of developers in another country where you don't have control over the methodology they're going to use, you're going to get the standard methodology that comes with that language. So C# plus its standard methodology, especially, that's a few years old now, so C# is improving as a language all the time, and largely due to the pressure that F# is kind of putting on it, or the positive influence that F# is putting on it. But as it was then, and I think still normally in most places around the world, C# methodology is still very heavily object-oriented. You have lots of people just taking standard Java methodology and coming over to C# and applying it in its full extent. And so, no, I wouldn't quite separate those two. So I would say, but you can definitely use C# in a much more functional first kind of way. It's still, I've done some C# programming recently, and I've got to say it didn't feel like you're landing in that sweet spot of functional first programming with F#. So yeah, but does that answer your question? Cool, thank you. One final question? Okay.
So some of the kind of worst practices you gave were language features. Why not explicitly deprecate kind of patterns that people misuse?
Oh, we should. It's costly and it takes, deprecation is not an easy thing to do. It's perhaps especially in a context of, Microsoft have traditionally cared an awful lot about backwards compatibility and But yeah, there are absolutely things I want to deprecate from F# practice. I've already mentioned some, just 2 small examples of that. There'll probably be about a page of further examples of things. So yes, we should do that. It's just every time you have a deprecation discussion with a team, people just bring up hundreds of reasons not to deprecate. They're nearly always to do with backwards compatibility in some way. But if you get deprecation wrong, then if you make a mistake in deprecation, you make the error too strict, then the cost is quite high. If you end up in a churn where you deprecate and people complain about deprecation because you have forgotten some little angle on where that thing gets used, and then you have to re-enable it, and you go backwards and forth, and nobody knows where you stand. That's really the only reason why we don't do it. It's just the cost of doing it. Right. Thank you.